Okay. Yeah, the Lorentz model is extremely important because first of all, it's so easy to use, and it turns out that with some, I mean, it's a great picture to have in your mind, and it's extremely easy to patch up quantum mechanically. Like, so it actually gives you quantum mechanically accurate results, which is remarkable. I mean, sometimes, the physicist approach is try it. If it works, then great, and we can understand things later. And that's definitely a lot of the times how experimentalists and theorists work together. And that's why to this day, I mean, we don't really know exactly what an electron looks like. I mean, no one's imaged it, no one's imaged uh, protons and things like that, but we're able to do so much with them. We're able to manipulate them, we're able to predict how they behave under certain extremely counterintuitive conditions, and it's all because we're prepared to. Uh, there's a bit of a pioneering instinct there that like uh, some daring, that we're prepared to go forward, even if we don't quite know exactly what we're doing. And I guess that's a very human thing. Okay, so let's continue with this model. It's a very important model, and also so simple, so simple. Uh, Let me remind you about this. Uh, when you pull this away from its equilibrium point, then there's a restoring force, if you remember, and this F restoring was proportional to the displacement away from equilibrium, right? So it's proportional to x, and of course the restoring force, then the constant of proportionality is the spring constant, right? The stiffer the spring, the more the stronger the restoring force, and of course it's opposite to the displacement. Okay, so here x is the displacement from equilibrium. Okay, so so in fact, I mean, so what I mean is that this x is the compression or extension of the spring. And then the other thing I want you to remember from simple harmonic motion and all that was that there was something that we defined as the, let's denote it by omega naught, and this is the natural frequency of the spring mass system. Okay, meaning that if I were to pull the mass out and then let it go, right? Pull it out, let go, then it would bing bong back and forth at a frequency that is determined by the spring constant and the mass, because this natural frequency is equal to the square root of the spring constant divided by the mass. Okay, so there were these two things that were the hallmark of the spring mass system. So simple harmonic motion of the spring mass system. Okay, so this is something we've studied before. And that's what Lorentz wanted to apply here. Okay. There are two assumptions that he used. So we should write those down. Two assumptions behind the Lorentz model. And, so the first one is that when the atom interacts with light, then the electron, so this is something he postulated, I guess is the word, that the electron is the lightest part of the atom. Okay, so it's the lightest, and he knew, he had access to these experiments at that time, I guess was it Chadwick or someone who had uh, determined that the, some type of I mean, besides knowing that the electrons exist, they knew that this was I guess this was a fair assumption for that. As it turns out, it's a good assumption. I'm not sure exactly what he knew at the time, but electron is the lightest part of the atom, um, that I mean, so is the lightest part. So that's the only. So that's the only part that really responds. Like the nucleus doesn't respond much; it's so heavy. So the electron is the one that wiggles. The nucleus maybe wiggles just a little bit, but it's so heavy that you can ignore it. So you only need to know uh, the response of the electron to the E field. Okay, and also the fact that if you look at the model, you're just looking at this one electron going back and forth. This is also another reason why physicists love alkali atoms. Okay, because alkali atoms, you have just that one electron, easy to model, um, and there are other reasons which we don't have to go into right now, I suppose. I guess the other big reason, besides the fact that it's simple to model, I mean, since we're going into it, I'll just give you the two big ones. That physicists um, love alkali atoms because the single valence electron uh, fits the Lorentz model, and which implies that alkali atoms are easy to model. Alkali atoms' response simple to model. And the other thing, which is not so obvious, I guess, is that the single valence electron, you can make transitions from the ground state to higher states, and these are transitions out from the ground state uh, to higher states, and you can make those transitions with relatively lower optical energy. So you don't need strong excitation to make the atom go into excited states. So um, uh, transitions can be excited using low, and of course what's low, what's high, but I'm using low optical energy. So I'm just going to say using relatively low optical energies. Okay, that's something that we don't have time to go into right now, but alkali atoms, that's why they're easy to excite and they're easy to model. All right, so that's the so anyway, so that's one assumption. So that's why we're only looking at the electron. And the other assumption is something you know already, that the motion of the electron, as it goes back and forth, or as it was going around the nucleus. This is a 1D model, so, but I mean, whatever. The motion of the electron is non-relativistic. That's something we've already. And you know why he assumed the motion of the electron to be non-relativistic? We proved this in the last lecture. But you know why Lorentz assumed this to be non-relativistic? There's a totally non-physics reason for that.
Relativity wasn't invented yet.
Yeah, 1892. Nobody even had heard the word relativity at that point, so he didn't know any better, and it turns out that worked anyway. Okay. So now what we have to do is basically write out, and it will be back to good old Newton physics for light atom interaction, and we'll come up with all these gorgeous predictions about, we'll understand why the sky is blue and sunset pink and all that kind of stuff. So it's really nice, and it's a very nice, easy theory. The end goal is to have microscopic formula or a formula for the P field, the electric polarization, because that's what's different from vacuum. And if we have a expression for the electric polarization, but in terms of atomic variables, you know, then maybe we can. I mean, all this is still good, but we will have new physics, and we need to combine it with this in order to have a microscopic consistent theory. A microscopic theory which is consistent with Maxwell's equations, and it will lead us to new insights. Now, let me set it up, and we'll just go as far as we can, and then we'll stop in about 8 minutes or so, right? So here's the equation itself is extremely simple. Let's write it out. So we're just, this is how easy it gets. Can't get easier than this. We're actually going to apply F equals ma to the oscillating electron. Okay? And so the right hand side is easy. It's just, R. Okay, so basically it's displacing out, like this coordinate is R, let's say. Okay. Now I am going with a one-dimensional model here, so maybe I'll replace this with an X. Okay, so that's why this I'm saying is X. Okay, so 1D. All right. And so because it's, yeah, I mean, I could have stuck with R. Doesn't matter. Well, anyway, it's a 1D picture. So there you go, X. All right. Now you might say, well, but why have you left a vector sign on there? And yeah, I mean, everything's happening in this direction. Okay. It could be any direction. Let's just call that X. Anyway. What about this force? Well, who are the forces acting on this? Remember, it's just the Lorentz force because there's a charged particle being acted upon by an electric field. So it's the Lorentz force, and so the charge is E, okay? And this electron charge is negative, so E is negative. But anyway, so E, and then you have the electric field plus the velocity cross B. We're sticking with SI units just because that's what we've done the entire, like that's what, all our other formulas are in SI, so we have to stick with it. All right. So there's the Lorentz force, but now the only difference is that you also have the fact that the electron is tied to the origin in some way, to its equilibrium position, right? So this is the equilibrium position, and it's tied to that. And of course, and we know that it's as if it's tied to the nucleus through the electrostatic force and things. So, there's a restoring force minus Ksx. Okay. So, so there you go. That's all there is to this. Um, and remember, this is the displacement from origin, the origin being the equilibrium position. Okay, uh, we can neglect this because V is non-relativistic. This we've seen, we saw this from our Gaussian unit argument. Previous arguments. Okay, and so the equation becomes m double derivative with respect to time is equal to, you have electric field, okay, and this electric field is a function of x. Now let's be careful now. X and t, let me write it out and then I'll tell you. Minus k sub s x. Okay, and this is a function of t. This is a function of t. I want to be careful here. This electric field is a function of x and t, but this is not the x that, you know, it's the electric field is a function of x, but it's not this x. This x is the displacement of the electron from the origin. This is just a generic, I mean, the electric field is a function of space. Okay, so this is a function of r. Okay, I mean, that's the electric field coming in, a function of r, space, and time. Now, the reason I don't, the next thing that I'm going to say is that because of the long wavelength approximation, the electric field over the size of the atom, okay, over the extent of the atom, the electric field does not have any spatial variation, meaning that all these crests and troughs that I've drawn here, well, the atom, the entire atom, is so small that it only sees either the crest, the whole atom will see a crest. So the electric field is the same everywhere. It's not like the electric field is different from one point to another point inside the atom. It's the same exact electric field, and it is whatever it is at some point on the wave, right? Some point on the wave, some point on the wave. There's no variation of the electric field across the size of the atom, which means that I can neglect this spatial variation of the electric field over the extent of the atom because of the long wavelength approximation. Long wavelength approximation. Okay? And what it's saying is that no spatial variation of the electric field over the size of the atom, over the extent of the atom. So the final equation that I have, and actually let me also divide across by m, because you see I have this natural frequency here, and the thing that I want to also say is that it is a little ridiculous, you have to admit, that I have things like a force constant of a spring inside my model, and I don't like that. I mean, because there is no spring in there, so I want to get rid of it. So I'll divide across by m. Okay, and now I can replace this with omega naught squared. And I like that because, you see, there is no spring that exists inside the atom, obviously. But there is this concept of the natural frequency, which if I can sort of talk about it in modern parlance, this is actually real. There is a natural frequency, meaning that now, I mean, if you think of the the nucleus, okay, with an electron going around, and it is a reasonably valid picture that, when you have a electromagnetic wave, and again, it's all exaggerated. These crests are minuscule compared to, anything. Sorry, the distance between the crests is huge compared to what I've drawn here. But I have to show a wiggly electromagnetic wave coming in. And it's a reasonable picture to assume that if this wave comes in, let's say it's a pulse, and it kind of whacks the atom, right? And then the electron goes around, it's like a string on a guitar that got plucked, right? And so it does this number. And all of this is, so I mean, the idea is that if a pulse whacks it at a certain frequency, then, and then the electron kind of rings, back and forth. And those are the sort of transitions we're talking about, where here it's allowed to oscillate on its own. The natural frequency at which it does that is this omega naught, okay? And of course, if the wave is on all the time and it keeps exciting the atom, then it goes back and forth about its equilibrium position. And here the equilibrium position was right there, right? And it goes back and forth about that. And that's the displacement x that we're talking about, right? So this is a modern sort of justification, or another picture that can be superposed on top of the original picture in 1892. All right. So this actually has real meaning, and the electric field will have its own, because we'll write out, we might, and I'm going to end now in just a minute here, less than a minute, that we will assume this to be a plane wave, just for simplicity. Assume plane wave. So this would be, the electric field would be, there is some polarization, there is some amplitude, and then it's a e to the I, k dot r minus omega t, right? Now we've already said that we're neglecting the spatial variation, so this we can throw away. But you see, there's this driving frequency omega. So there's a natural atomic frequency omega naught, and there is a driving frequency omega from the electromagnetic wave. Okay? And so there's two frequencies, and so now there will be things like resonance and stuff. These frequencies are real. They actually are observable in life. And, so the omega naught is a real thing, but the k sub s is not. All right? And so now that I've removed k sub s from the equation, I actually do have a realistic equation. So here's my last, I'm just rewriting that equation in terms of realistic quantities. Yes, there is an electron mass, there is an electron charge, there is a driving field, and you have omega naught squared x. And this is all nice and real. Okay? So this will be the Lorentz model equation for the atom. And that's where I'm going to stop. In the next class, we will solve it. And we all know how to solve it. It's a trivial solution almost. And then we can see from that what we can get out of it. Okay? So I'm going to now stop